So we're going to do our second example on Newton's universal law of gravitation. So this example is a factor change problem. We're going to figure out how does the factor F change if we were to change the distance between two planets. So if we were to double the distance, triple the distance, or double distance and one mass is doubled as well. Okay, so let's go ahead and solve these one at a time. So these are factor change problems, so we want to make sure that we write down the change first. So for part A, the radius is becoming 2r. So we want to write our equation so it has 2r instead of r. G m1 m2 over 2r squared instead of r squared. So we want to pull out that other factor that we've now added to our equation so that we end up with our same equation we started with. That's the original equation. So if we have 1/4 on the right-hand side, we need to have 1/4 on the left-hand side. So our final answer is decreased by a factor of 4. Okay, or you could write it as f over 4. But what this means is when the value is less than 1, it's always decreased. When the value is greater than 1, it's always increased. So this is decreased by a factor of 4. Okay, part B. Now we are changing r to 3r. So I want you to go ahead and do this problem on your own. So pause the video and then check back in with your answer. Okay, you get 1/9 on the right-hand side, which means we need to have a 1/9 on the left-hand side. So we are decreasing f by a factor of 9. Okay, for part C, we have two different things changing. We have the radius is doubling, and one of the masses, let's just say mass 1, is doubling as well. Okay, so for our equation becomes G 2m1 m2 over 2r squared. So we're left with a 2 in the numerator. Let's pull that factor out, and a 2 squared. We get 4 in the denominator. G m1 m2 over r squared. So if you have 2/4, which is also equal to 1/2 on the right side, you need the same thing on the left side. So we are decreasing by a factor of 2, or f over 2. Okay, there is one more problem I want to show you. So I want to show you how to find what the acceleration due to gravity is. We're going to call this little g. Okay, so it's the little g, it's not the capital G for the gravitational constant. Okay, so how we're going to do this, we're going to set up a scenario. We're going to say we have a person standing on Earth. He holds a ball 1 meter above Earth. Okay, and we're going to find what gravity is. So we know that we could find the force due to gravity of the ball. We know that. We know the weight of the ball is mass of the ball times gravity of the ball. Okay, we also can find force due to gravity between the ball and the Earth by using our new equation. Force due to gravity equals gravitational constant, m1, we'll call m1 ball, and m2 will be Earth over r squared. So it's really important that this r we talk about is going to be the radius of the first mass plus the distance between the two masses, so ours is 1 meter. So radius of Earth is 6.38 times 10 to the 6 meters. So our total radius is going to be 6.38 times 10 to the 6 meters plus 1 meter. But since this number is so large, this 1 meter doesn't even have an effect on it at all in scientific notation. The final answer is still 6.38 times 10 to the 6 meters when we add 1 to it. Okay? So let's go ahead and set these two things equal to each other, two force equations. We have mass of ball times gravity equals gravitational constant, mass of ball, mass of Earth, over r squared. Mass of ball cancels. You're left with G, acceleration due to gravity, is G m Earth over r squared. Okay, so when we plug in our numbers, we get 6.67 times 10 to the negative 11 times 5.98 times 10 to the 24. So you will be given the mass of Earth, which I just gave it to you in the equation. Oops, that's 5.98 times 10 to the 24 kilograms divided by our r squared. Our r squared is 6.38 times 10 to the 6, and that's squared. Okay, when you plug this into your calculator and make sure you actually go ahead and do it, you get 9.799, which we round, we get 9.8 meters per second squared.